All right, so this is what we'll do generally speaking as we go through class. So when we introduce a new topic, I'll have some guided notes. This is what we're going to cover today. I'm actually borrowing these from the other Dr. Stiggles. She has her students watch a video ahead of time and fill these out. We're just going to talk about it in class and go through them. Spend probably 15, 20-ish minutes around there, and then the rest of the time will be devoted to working on problems. Reinforce what's going on. So that's how a typical class day is going to go. If for some reason you miss class, I will record lectures. Well, I'm doing it on the screen rather than doing it on the board. So we can record it, and it'll be on Moodle. I'll post a link to the video on Moodle as well as any of the handouts that go on that day. So you'll have those. All right. So this stuff might be some review for you, but let's just go over some things. So one of the basic building blocks, if you will, of algebra, and even going in higher mathematics, are what we refer to as polynomials. So it's important to know what the definition of a polynomial is and what the pieces are so that we are all on the same page with the language. Like I said, they're kind of like building blocks, right? So back in grade school, you talked about working with whole numbers to start with, and then you started doing some fractions, right? Added some fractions in there, and then you started doing things like doing square roots and all those kinds of things, right? But you built up with the whole numbers. So from an algebraic sense, the polynomials are the whole numbers, and you build up from there, okay? So to talk about what we mean by polynomial, we need to talk about the individual pieces first and then how we put them together. So that's what that monomial part here is talking about. So the monomial is the individual piece, okay? So if you have something like 3x to the 7th, that's an example of a monomial. So when you see a monomial, there aren't any plus or minus signs in there, okay? A lot of times the monomials are what we refer to as the terms, because term has a lot fewer syllables than monomial does, okay? So when you have the no pluses or minuses, right? Just number times the variable piece, that's what we mean by a term, okay? So this would be an example of a term. And again, the longer word is the monomial. This number that's in front, the part that's multiplied, that's referred to as the coefficient of that term. That's the number we're multiplying by the variable. Now this is the exponent on the x, and we're going to review exponents in a minute. But another word for the exponent when we're talking about polynomials or monomials, that's what we refer to as the degree. So that's the degree of that term, the degree of the 7th, of the monomial. So a lot of times, if I'm talking about individual terms in a polynomial, I'm going to refer to the exponent term. So what I mean by that is this would be the 7th degree term. Okay? It's the one that has the x to the 7th power on it. Okay? That's what I mean by that. All right. So when we have a polynomial, we put together a whole bunch of monomials together to make the polynomial. The polynomial has several coefficients, but the one and several terms, several coefficients, several degrees on it. But what we're typically interested in is the one that has the highest degree, the highest power that we see. Okay. So when we have something like a polynomial in this case, maybe I write down 2x cubed minus 7x squared plus 5. I've put together 3 monomials, right? Here's a term, 2x cubed. Here's a term, minus 7x squared. Here's a term, 5. Okay. I put those terms together, made a polynomial by doing this adding and subtracting. So basically, I'm adding. I can think of this minus 7 as a plus a negative 7. So we form bigger polynomials from these building block monomials, if you will. Okay. As far as the polynomial goes, one of the important things we look at is the highest degree term. the term that has the highest x power that we see. Okay? In this case, this is the highest, right? So the degree of this polynomial is 3 because that's the highest power of x we see. The coefficient that's on that term we refer to as the leading coefficient. So that's the coefficient on the term that has the highest power of x. Leading coefficients and degree are important pieces of information to get from a polynomial later on when you try to start analyzing what's going on with a polynomial. That's way farther down the road, okay? But that's why we care about these things. They give you helpful information about the polynomial. Pardon me. So let's just do another example here off to the side, and we'll get to talking about adding and subtracting here in a second. But let me just do another example off to the side. If we had 6x squared minus 9x to the fourth minus x to the fifth plus 12. First, how many terms does that polynomial have? How many individual terms are there? 4, right? There's 4 terms, right? There's an x squared term, there's an x to the fourth term, an x to the fifth term, and then we've got that plus 12 on the end. We typically refer to that as a constant term. Right? So there's 4 terms on that one. Now, the next question I'm going to ask you is, what is the degree? Remember, degree is highest power of x that you see. 5, good. We typically write polynomials where the powers go down, right? But they don't have to, okay? They could mix them up on you, right? So make sure that if you're asked for degree, you really are looking at the biggest, not what's written first, okay? That's important. Pardon me. Now, what about the leading coefficient? So remember, the way that's defined is I have to go to that highest degree term, which is here, right? You just told me the degree was 5. What's the coefficient on that term? You gotta be a little bit careful. Get that minus sign in front. It'd be -1, yeah. Okay. So again, I know it's a little bit misleading to be funny, right? It's a little bit misleading. Leading you usually think is first, right? But that's not what it means for a polynomial. It means that the one that's on the highest. Okay. So we're looking for that coefficient. And if there's a minus sign, make sure you include the minus. Okay. Yes, the highest on the x-line. Yep, the highest. Yep, it's the one that's on the highest degree. That's exactly right. You got it. Yep. All right, so let's talk a little bit about how we add and subtract these things. So again, we said that we also call binomials terms. So the way that we add and subtract polynomials is that we combine what we refer to as like terms. Now, I'd be a little bit careful. What do we mean by like terms? Okay. So the term, again, is a monomial. All we mean by like terms is these are terms that have the same degree. It's all going to be my like terms. So if they have the same degree, they're like terms, and those are the ones we're going to put together. If they don't have the same degree, then we can't add and subtract them. They're different terms, so we can't combine them. Okay? So let's look at, pardon me, this first example. We've got this polynomial, the 7x cubed plus 8x squared minus 2x plus 1, added to the polynomial 6x cubed plus 9x plus 4. Okay. First, let me just ask you the individual questions we mentioned a minute ago. For this first polynomial, the degree is 3, and the leading coefficient would be 7. Good. For the second one, the degree is 3 again, right? That's the highest power, and the leading coefficient for that one is 6. Good. Good. You get the hang of that. Wonderful. All right, so again, now we're looking for like terms. So what I mean by that is both of these terms both have x cubed on them, right? So those are like terms. When you have like terms, you can combine them using addition and subtraction. And it's pretty straightforward. Think about them as kind of like apples ideas. I've got 7 apples and 6 apples. How many apples total do we have? 13. That's exactly what we just add the coefficients as we go along. So we have 13x cubed. When we add, we're not changing the exponent at all. Okay? We're just combining the coefficients together. Okay? What's another pair of like terms? Good. The 8x squared and the 9x squared. When we combine those two, good. 17x squared. Good. Is there anything that's like the negative 2x in the other one? No. So we'll just have negative 2x then. There's nothing to add or subtract to it. The last set of like terms are 1 and 4. We add those together, we get 5. And again, that's as good as we can get. These terms that were left are different. So I can't combine them. It's as good as it can get. All right. Let's look at the subtraction. I would do something first before I even try to subtract. What I would do is I would take this negative sign and I would distribute it to all 3 terms to start with. Okay? I think it just makes it a little bit easier. You don't get confused with the signs. So the first one here, that doesn't change the first one at all. But this one, when I distribute the minus sign through, I get minus 5x cubed. What's going to happen to this one? It'd be a positive 2x, good, and then a negative 1. Now tell me a pair of like terms. Now tell me a pair of like terms. That woke me up a little bit. Can you tell me one pair of like terms? Yeah, the 6x cubed and the minus 5x cubed, right? So we combine those two, what are we going to end up with? Yeah, so it's just going to be an x cubed, right? I do the 6 minus the 5? Right. Or plus it would be 11, that's right. So we would get x cubed, right? Because we're doing the 6 minus the 5 there. What else do you see? Good. I see the negative 9x and the plus 2x. So negative 9 plus 2 gives us negative 7x. And then finally, plus 6. Good, because we're going to combine those two pieces. That makes sense? We're going to practice these more as we go along. Is that okay? All right. The next thing we're going to talk about a little bit is multiplying polynomials. Before we multiply polynomials together, we better multiply just some pieces together. So just remember, so a little bit with exponent stuff. We already talked about what an exponent was a little bit. But all we mean by an exponent, which is what this first blank is, it's just a shortcut to represent repeated multiplication. Okay? And just to make sure that we're all on the same page with what the terms mean, this top piece right here, that 3, that's your exponent. And that tells you how many times something is repeated. Okay? The bottom piece, this part here, that's what we refer to as the base. That's the piece that is being multiplied by itself. Okay? So this one is telling me that the 4 is multiplied by itself 3 times. Yeah. Mm-hmm. I don't care. Yeah. You can put a 1 in front of the x. That's perfectly fine with me. Okay. So if I look at this x cubed, so the base is a variable. What in terms of multiplication, what does x cubed mean? So it just means that it's, so like this is 4 times 4 times 4, so this one would be, yeah, the x times x times x. It just means we're going to multiply the x times itself that many times. That's all the exponent means. All right. So this next little bit is just to try to get us to the point where we can see what happens when I take 2 of these things and multiply them together. What happens with the exponents? Okay. Pardon me. So first, let's just do this in stages. What does this 2 cubed mean again? What would that mean? 2 times 2 times 2, right? And then I would still have a 2 to the 4th here. Oh, yeah. Yep. Okay. So this part right here was the 2 to the 3rd, right? The 2 to the 4th would mean what? Yeah, the 2 times 2 times 2 times 2, right? Okay, so the first one means we multiply 2 by itself 3 times. The second one means we multiply 2 by itself 4 times. So looking at this line now, how many times did we multiply 2 by itself? 7 times. Good. So our 2 cubed times 2 to the 4th is 2 to the 7th. Well, how does that 7 here relate to the 3 and the 4? Yeah, it's addition, right? We had 3 of them and then added 4 more of them to it. You got a total of 7, right? So this is what we call this a law of exponents. It's one of our laws of exponents. Now, what's important about this is that you have this base has to be the same. Okay? If you have different bases, you can't do this. Okay? Has to be the same base. Right? When you multiply, you add your exponents together. Okay? So this is important when you multiply polynomials together. We need this rule to help us multiply polynomials. Okay? So let's look at this first example. And I'm actually going to rewrite it first and then simplify it, okay? You don't have to do this every single time. I just want to illustrate what's going on, all right? I have 2 monomials together, and I'm going to multiply them, okay? When I multiply the monomials, you'll multiply the coefficients together, and you'll multiply the variable pieces together. All we're doing there is using the fact that it doesn't matter what order I multiply things in, right? I'm just rearranging. Okay? So I rearrange, I'm going to multiply the coefficients, and then I'm going to multiply the variable pieces. Okay? When I multiply the 2 and the 5 together, what do we get? 10. Okay? Now, what did we just say we do? Are the bases the same here? Yep, so when we have the bases are the same and we're multiplying, what do we do with the exponents? Add them, and we get x to the 6th. Good. Okay. So again, you're going to multiply your coefficients together, and then you will add the exponents on the variable pieces together when you multiply these. Okay. So now we're going to use this to extend to arbitrary polynomials and get them multiplied together. It seems like it's complicated, but really all we're doing is just doing the distributive property over and over and over again. Okay? So what we'll do first is I'm going to take this 4x and I'm going to distribute it to every single term first. So I'm going to write it out longhand. As you get more practice, you might be able to do a couple of steps at once, but let's just do it a step at a time so we all see what's going on. I would have 4x times 3x squared for the first one. I've got 4x times 2x for the second one. And I've got 4x times 5 for the third one. That's what we mean by the distributive property. I'm taking the thing that's multiplied out in front and distributing it to each of the terms in the second one. That's what we mean by distributive property. Now that we've got it distributed, now we can multiply these together just like we did in the previous example. Okay? What do we do with the 4 and the 3? Multiply them and make it 12, right? And then what do we do with the exponents here? Add them. This is understood to be x to the first, so we get x to the third. Good. What do you get for the second one? 8x squared, and the last one will be 20x. Good. Because again, we'll take the 4 times the 2 to give us the 8. 1 plus 1, it's an understood 1 up there, right? 1 plus 1 gives us the 2. Over here, the 5 times the 4 is 20, and there was nothing else to multiply the x by, so we just still have the x. We okay with that one? Okay. All right. We can do the same property to multiply two binomials together. Binomial means a two-termed polynomial. That's all binomial means, is there's two terms in the polynomial. If you see the word trinomial, that means there's 3 terms. Okay. They're all examples of polynomials, but monomial means 1, binomial means 2, trinomial means 3. Now you may know, you've probably heard the acronym FOIL before, and you can use that here, but I just want to show you where it comes from. Anytime that you do multiplication of polynomials, you got to make sure that every term in the first one gets multiplied by every term in the second one. Okay, that's the distributive property. So I'm going to do this out longhand, if you will, to illustrate where that FOIL, if you've heard of FOIL, that's where the FOIL comes from. But really all we're doing is distributive property. Okay, so first, I'm going to treat this like it's one whole thing, okay? I'm going to take this big chunk and I'm going to distribute it to here and to here. When you distribute it, you'll have 2x plus 5 times the 4x, and we'll have the 2x plus 5 times the 3. That's just the distributive property, exactly like we did in the first example, right? What did we do in the first example? We took the first thing and multiplied it by all 3 things. Right? So what I did here, I took the first thing, that whole big thing, and multiplied it by everything else. Okay? Now I can do the exact same thing with these pieces. I can take the 4x, distribute it. I can take the 3 and distribute it. So we get 2x times 4x plus 5 times 4x plus 2x times, I'll put parentheses around it so I'm emphasizing what I'm multiplying. 2x times the 3, 5 times the 3. So when we multiply binomials together, really we're using the distributive property twice. First time to get the first chunk through, second time to make sure we get the second chunk through. Okay. But notice what I said about when we multiply polynomials. I got to make sure that everything in the first polynomial gets multiplied by everything in the second polynomial. Notice the 2x here gets multiplied by the 4x and the 3. The 5 gets multiplied by the 4x and the 3. Okay? So everything in the first is multiplied by everything in the second. Okay? So we had 2 things in the first, 2 things in the second, we get 4 terms. If we had 2 things in the first and 3 things in the second, we would get 6 things. And so on down the line. Okay. Now we can simplify. What is 2x times 4x equal to? 8x squared, good. 5 times 4x is the 20x, good. 2x times 3 is the 6x, good. And then 5 times 3 gives us 15. Do you see anything that gets combined? Yeah, we have the 20x and the 6x are like terms. So you get 8x squared plus 26x plus 15. Again, like I said, you've probably heard the term FOIL before. That's just a way, it's a mnemonic way to keep track of all the multiplications you have to do. So your FOIL stands for, just to tell you what it stands for. This stands for first, outer, inner, last. Okay? This would be your firsts. All right? The first term in each binomial. The outer in the binomial. The inner in the binomial. And the last in the binomial. So this is your FOIL. Acronym's not that important. Again, the rule is the distributive property. I have to distribute everything in the first polynomial to everything in the second polynomial. That's what the rule is. Okay? FOIL is just a way to make sure in your brain that you've got all the distributions done correctly. That's all they use the word FOIL for. Okay? But it only works for binomial times binomial. If you've got bigger polynomials, you literally have to go through and do the distribution. All right. Questions on that one at all? We're going to do some more practice here, but make sure we have all on the same page. So let's do a couple of these together, and then I'll let you go to town on practicing some of these. All right, so let's go through a couple of these together. Like I said, make sure we're all on the same page. And then I'll let you practice. I'll come around the room and answer any questions that you have as you're practicing. Let's do a couple of these together, though, and make sure that we're all, like I said, all on the same page, and then I'll let you go nuts. Let's look at part D together real quick. D. Let's look at part D here. In this part D, we're subtracting 2 polynomials. So what did I say you probably want to do first to make sure you don't mess up your signs? Yeah, distribute that minus sign through, right? So I'll have 14x squared minus 2x minus 9, or minus 8, sorry. What do you get when you distribute the minus sign through everything? Yeah, minus 6x squared minus 7x plus 13. Good. I would do that first to make sure you don't mess up your signs. Because that minus sign has to apply to everything. I would just get in the habit of distributing it through everything. And that way you won't mess it up. It's easy to mess it up, so I would do it that way. All right, so now what can we combine? Yeah, the 14x squared and the negative 6x squared gives us 8x squared. Good. What else can we combine? Yeah, the negative 2x and the negative 7x gives you negative 9x. Good. The negative 8 and the positive 13 gives you 5. Good. That's how that one would simplify. Again, like I said, if you see a minus out in front of the parentheses, my suggestion would be distribute it first. Okay, just to make sure you don't mess it up. If you're okay handling it as you go along, that's fine. I'm just saying, my suggestion would be to multiply it through and make sure that you get it. Let's just review these a little bit. Let's look at number 3 that's on the second page, just real quick. Make sure we're on the same page. Let's look at part B on number 3. We did an example of this earlier, but I just want to make sure we reinforce. When we multiply the 4x squared and the 7x cubed, what are you going to end up with? 28, good for the 4 times the 7, and then x to the... Yeah, so remember we got to add those exponents, right? So we'll get x to the 5th there. Right, we'll multiply the coefficients and we'll add the exponents together. So let's look at part A in the next problem. Like I said, I'm going to leave the rest of these for practice. I just want to make sure we're all on the same page with these. Let's look at part A. This one just has a monomial times a binomial. What do we want to do with that 2x squared? Distribute it, good. So I'm going to write it out longhand here. We'll have 2x squared times 3x squared, and then minus 2x squared 4y squared is what we have, right? Multiplying it by the first one, multiplying it by the second. What do we get with that first one? 6x to the 4th, because it's 2 plus 2 there, right? Yep, so 2 times 3 gives us the 6. 2 plus the 2 gives us the 4. What about in the second one? So we got so this is multiply here, so we'll have the 2 times the 4 gives us 8, right? Can I combine the x squared and the y squared? Are those allowed to be combined? No, because remember we have to have the same base to be able to do anything, right? So the best we can do is write x squared times y squared. There's nothing else we can do with that as far as it goes. Okay. Any question on that one? I know that was a little bit trickier, right? But remember, in order to use the law of exponents that says we can add the exponents, we absolutely have to have the same base. And these have different bases. All right, go ahead and work on these. Like I said, I'll be around to answer questions. Okay. I will have all the answers to these practice problems posted on Moodle this afternoon. So if you don't finish up here and want to practice later, you can still look at them there. But like I said,